Okay, so we're looking at paired hypothesis test. So Professor Andy McNeil measured the time in seconds required to catch a falling meter stick for 12 randomly selected students, dominant hand and non-dominant hand. Professor McNeil claims that reaction time in an individual's dominant hand is less than the reaction time in their non-dominant hand. And they ask us to test an appropriate hypothesis and state our conclusion. So we need to make a decision. Since we're looking for an average, we need to define our parameter. In this case, mu d, and it equals the true population mean difference in reaction time, and we need to define how we're going to do that. And in this case, we'll just choose dominant minus non-dominant. We could have chosen the other direction, but I'm going to go dominant minus non-dominant. All right. Well, McNeil's hypothesis is that if you took the dominant and the non-dominant, that the dominant was going to be less time than the non-dominant. And it's real important to show this step because it'll help you out in writing your null and alternative hypothesis. So every time we do a test for differences, it's going to be the differences equal 0, that there's no difference in reaction time. However, our hypothesis was that there is a difference. Our McNeil's hypothesis is there is a difference, that mu d is less than 0, and I know that because I said dominant is less than non-dominant. All right, so this, however I do this inequality, is what I'm going to have for my alternative. So this HD, this should have been HA, not HD. Then we have our conditions. And we have a random sample as our first condition. This is just a random sample of McNeil's students. All right. Then we need to test to see if there is, then the next thing is it less than 10%? So n is less than n divided by 0.1, or the sample is less than 10%. So we have, in this case, we have 12 students, which is 12 divided by 0.1 equals 120. And it's reasonable to assume that Mr. McNeil has at least 120 students. He's a good teacher, very popular. Never met the man. All right. The next thing we need to worry about is whether or not our data is normal. They didn't tell us the underlying data is normal, and they didn't. We don't have a sample size of 30, so we have to check to see whether or not it's normal. Well, what I'm concerned about being normal is the differences. I'm not actually concerned about whether a dominant hand is normal or non-dominant, but whether the differences between the two, dominant minus non-dominant, whether that is actually normal. So to go back to do that, I need to enter the dominant hand. I need to take the dominant hand and I need to enter this into L1 and this into L2. All right, so stat edit, and I've entered all that data into L1 and L2. Then very carefully go to the very top of L3, and I have dominant in L1, non-dominant in L2, and I go to the top of L3 and I'm going to go second 1. So L1 minus second 2. So L1 minus L2. And then it populates those differences. So basically this minus this equals negative 0.002. This one divided by this one, minus this one is 0.008. So we have all the differences listed. So now that I have the differences listed, I need to go ahead and do my box plot. So second stat plot, press enter, make sure it's turned on, highlight the box plot that actually shows outliers. We need our X list being L3, so second followed by number 3, so it's L3. Frequency should be 1. And then we're going to press zoom 9. And when I look at it, it's like, well, that's kind of weird. But if I look at this distance versus this distance, about the same. I don't have any outliers. So the box plot of the differences is reasonably symmetric with no outliers. Okay to assume normality of the differences. All right, so drawing that box plot, I'm just going to sketch it based on what I see, and what I see is something that looks a little bit like this. I'm not going to take a scale because I have ugly numbers, but if I go to the trace function, I find out that my minimum is 0.043, a negative 0.043. Then I have a negative 0.0235, a negative 0.0145, 0.002, and then 0.008. All right, so I'm going to go ahead and go to stat edit and then slide over to stat calc. And if I go to one variable statistics and make L3, I find that my X bar are my sample average of the differences. So the average of the differences we calculated in L3, X bar is negative 0.0132. I also find that my standard deviation of the sample is 0.0164. All right. So this is going to be a t-test. So t equals x bar d minus mu d over sigma d sd divided by the square root of n. Please note I'm using the sample standard deviation. So what I'm going to be looking for is the probability that t is less than, and I know it's less than because that's what I have as my alternative, than negative 0.0132 minus the claim of 0 over 0.0164 divided by the square root of 12. So at that point, stat test, we're going to run a t-test. So press stat test t-test. Make sure data is highlighted because we're going to use our data. Our mean was 0. We have list 3, so second 3, L3. Second quit. Stat test. 2's t-test. Highlight less than. Calculate. And I end up getting the probability that t is less than negative 2.776, and that needs in this case equals 0.009. All right. Well, that's my p-value. So my p-value versus my alpha. My p-value is 0.009. And if we use an alpha of 0.05, this is definitely less than. So we're going to reject the null. And I'm going to try to fit the conclusion in here. So our p-value is 0.009. Our decision, we reject the null. There is sufficient evidence at alpha equals 0.05 to suggest that what was our definition? True population mean difference dominant minus non-dominant is less than 0. All right. And then it's really great to have like a one-sentence conclusion as to what that really means. And I'm going to say McNeil is correct. The dominant hand is faster. Thank you.